Good morning, everybody. I hope you can hear us. I am Dimitri Pescia from Agora Energiewende, and I'm here together with my colleague Christian.
Good morning.
We are very happy to have you here, excited to have people from all over the world to follow with us this presentation on the study we released a couple of weeks ago. Before going into the topic, I want to give you some information, technical information, to be sure that the webinar will happen the best possible. We will have actually a webinar in two parts. The first one will be a presentation of the study, and then we will have a question and answers. In order to give your feedback or to ask question in the second part of the webinar, you will have to click on the down left corner on feedback, give feedback, and then you can actually click on question, and then you will be able to ask a question that we will select and give you the word. During the presentation itself, you can actually post comments, and we will take all these comments with us, bring them to the discussion. So you can find this little box, which is actually on the up right corner of your screen. And so don't hesitate to put any feedback during the presentation itself. For your information, we will actually record this webinar, and the first part, meaning not the Q&A session, but the first part will be then put online for being accessible later. So I think at this level we are really happy to present you this study, and I will start with it. You may, if you want to see better the whole slides, use the full screen mode that you find as well on the up right corner of your screen, which may be better to look at the slides. So let's go. Here we are. So this is actually the study we want to present to you. It's called the European Power System in 2030. It's a study, well, first of all, we are a German think tank, Agora Energiewende. We are actually based in Berlin. We are 19 energy policy experts, and we try to think about how to make the energy transition in Germany a success story by providing scientific assessments. We also implement dialogue platform like this webinar, for example, but as well live dialogue platforms in different formats. And our goal is really to put forward proposal to make this whole energy transition a success. The study we're going to present today is a study that is actually assessing what will be the future challenge of the European power sector in 2030, driven basically mostly by the development of variable renewables being wind power and solar PV. You see on these slides actually the objective of development of renewables in 2030 in Europe, and you see it's about 50% of renewable in the power sector generation, and 30% being wind and PV. The study we performed together with Fraunhofer IWES focused mostly on one part of Europe, being this Pentalateral Energy Forum region, which is encompassing 7 countries, Germany, France, the Netherlands, Belgium, Luxembourg, Austria, and Switzerland. And in this region, you have even higher share of renewables, which are foreseen by the energy policy targets, 54%. And 34 being wind and PV. So not only there is actually this political framework, but we believe this power sector transformation will be driven also by economic consideration, because you see in this graph, wind and PV have experienced a tremendous decrease in their costs, as captured, for example, by the LCOE. You see on the left part of this slide, the wind and PV generation cost is now in the range of conventional power plants. So we asked actually Fraunhofer to conduct a pretty in-depth model-based analysis to answer 2 questions. The first one being, what are the flexibility requirements needed to incorporate this large share of renewable energy in the power system? And the second question being how market integration can help to mitigate this flexibility challenge. So we'll present you the result of this study. This is our own interpretation of the study performed by Fraunhofer.
So I would like to, in the following now, present the main results of the study. First of all, I'd like to sketch the main pillars with respect to the modeling and methodological approach, which was performed by Fraunhofer IWES in order to address the project scope. So first of all, of course, since it was a quantitative study, input assumptions and data had to be selected, and this concerns the annual electricity consumption in the countries in 2030, the peak load levels, the installed renewable capacities, and the interconnector capacities linking the countries. The model itself is a two-step model. First of all, a disaggregated time series on an hourly resolution for specifically wind and PV is developed, and this is then linked in the second step with the load pattern, which is based on the 2011 load profile, and then these two informations are fed into the second model from Fraunhofer IWES, which models the European-wide power plant dispatch based on a simplified synthetic power plant park, still of course also assuming certain must-run levels per country. Also, a model feature is that the countries are modeled as national copper plates and are then linked through interconnector capacities. To start now with the first model from Fraunhofer IWES, the model to develop then in the end this hourly time series for wind and PV. The starting point is to utilize highly disaggregated meteorological data, so data on wind speeds and irradiation data, solar irradiation data for the year 2011. This is linked with the spatial distribution of renewable energy technologies, so where they actually installed, and how will this future deployment look like, linking these two information sources with the technical model of the PV plants and the wind turbine, then finally yields these hourly time curves for wind and PV on a spatial resolution of 8 to 46 square kilometers. With respect to the input data, the main data sources were for the countries of the Pentalateral Energy Forum region, the UK and Denmark, the national energy strategies and national network development plans. And for all other countries, we utilized the ENTSO-E system outlook and adequacy forecast, which is in line, the scenario 3, which is utilized in line with the 2030 targets with respect to climate and energy of the European Union. And I don't want to discuss all the data, but as we have already seen from Dimitri's part, in all the countries basically in 2030, the installed level of variable renewables, so wind and PV, is actually close to peak load. For Germany, of course, it's even above peak load because it has the most ambitious deployment targets. So we can already expect some quite significant changes to our power systems. Now, a second category of input required is interconnector capacities. I've mentioned already that the national power systems are modeled as a copper plate, so they are considered to be free of any domestic recongestion, but the countries are linked and coupled through interconnector capacities. And to derive the assumptions for these interconnector capacities, we utilize the ENTSO-E's 10-year network development plan from 2014. At the time of modeling, this was still in consultation as a starting point. And actually, if you compare it to the existing level of interconnectors in Europe, this TYNDP would yield a doubling of interconnector capacities. Now, in the past, basically, our past experience shows that typically projects are delayed with respect to cross-border interconnectors. Some of them are also then finally not built. So this typically yields a lag rate of 50% compared to the plan, and we also assumed this 50% lag to derive our, as we call it, probable scenario for the interconnector capacities, which still implies an increase in cross-border transmission capacity from 50 to 70 gigawatts. Now, all this information is put into the second model from Fraunhofer IWES, determining the actual power system and power plant dispatch. So we take the hourly load curve as a starting point, derive the feed-in from non-dispatchable renewables, and finally yielding a new time series, the residual load time series, which is the input to the power system model. And this residual load has then to be met by the residual power plant park, so the conventional power plants, and also hydro storage plants. And this dispatch specifically of the conventional power plants is modeled in a simplified manner. So a synthetic thermal power plant park is applied for all countries where different technologies with different electrical efficiencies replicate the economic dispatch in power markets. And then by taking into account also this interconnector assumptions, a total European-wide cost minimal dispatch is achieved, which then satisfied the residual load time series and can meet the power demand. It's important to point out that the modeling neglects additional flexibility providers. For example, pumped hydro storage is not modeled. I've mentioned that storage hydropower is modeled, but not pumped hydro storage, and also additional flexibility providers like demand response or new types of storage like batteries are also not modeled. And this then implies that our results or the modeling from Fraunhofer IWES is the conservative approach with a upper bound on the flexibility requirements. Now, what do the results tell us and look like? We've performed two scenarios in order to assess the flexibility requirements. One scenario where the countries are indeed linked through the NTC capacities, and one where they are in autarky, so every country has to be self-sufficient. And of course, wind and PV fluctuating in their output, because as they depend on the natural weather conditions, and with these increasing shares of wind and PV, it's obvious to expect increasing flexibility requirements. But the first important result is that the coupling of the power system helps. And to illustrate this, we will now watch a quick video, and I want to just highlight the main features of this video. In the upper left graph, you will see wind speeds as observed in a week in July 2011 moving throughout Europe, and then these wind speeds are translated by the model in the actual wind generation as assumed in our scenarios for the year 2030, and just here highlighted for Germany, France, the Benelux region, and Austria and Switzerland. And also then in the bottom left, you see the total wind generation in this region. So let's have a look at the video. As you see, this in this weather situation, the wind front is moving or entering Europe from the northwest, and you can see with the duration of wind power that these weather patterns imply that the generation changes from wind power is not the same in all the countries. Sometimes a country is increasing its wind speed, whereas it's rather constant in another country, so yielding a more total output in the region. And of course, also happens that they're going all over Europe, as is the situation right now in the video, and then of course we can also not benefit from any smoothing effects. But as soon as the weather implies different wind speeds, we can benefit from the smoothing effects. Can you switch to the So moving back to the presentation now, we have seen that due to and these decorrelated weather patterns are specifically important for benefiting from the smoothing effect from wind power. In this table, you can see the correlation coefficients between the wind generation in the countries of the Pentalateral Energy Forum. And it's interesting to observe that hardly these correlation coefficients are larger than 50%. And for example, to highlight the case of Germany and France, so the two largest countries in the region, then of course also with significant amounts of wind generation, the trends in the wind generation in two countries is only correlated with a correlation coefficient of 33%, and then indeed yielding the smoothing effects we have seen. This is also shown in this slide, where basically you can observe that through geographic aggregation, the total wind fluctuations get smaller. So we start at the level of 1 pixel. This is an area of 2.8 times 2.8 square kilometers. I'm sorry, I had to switch the microphones now. We start with, on the pixel level, with a resolution of 2.8 times 2.8 square kilometers. And you can see that the wind output is fluctuating quite heavily, so from almost no output to almost full installed capacities. And once we aggregate and sum up the wind power throughout the regions, the countries, and finally Europe, we end up with this last time series, which is much less volatile and lacks extremely high or low value. So the output changes of wind, which are then the challenge to the flexibility of the power system, get lower. And to illustrate this, when we look at the largest hourly wind ramps throughout Europe, that's minus 10% of the installed capacity. This means then that the residual power plant park has to provide a corresponding 10% ramp to compensate for that. But if countries would have to deal with this domestically, then for example in France, the largest hourly wind ramp is 21% of installed wind capacity, and then nationally this would require a response, of course, also of 21% from the residual power plant park. Also, this wind ramps, specifically the large wind ramps, occur only very rarely. So with the weather data from 2011, we see that only in 23 hours of the year is the wind ramp larger than plus or minus 5% of installed capacity. Not only can power integration facilitate these instantaneous moving effects, but we can also benefit from seasonal differences in the weather patterns. Of course, we know that in the summer months there is more PV generation than in the winter months, and it's just vice versa for wind. So if you take the total generation from wind and PV, we see that on a monthly basis it's much more stable compared to the individual technologies generating individually. Now, a second benefit from market integration is that we can utilize the wind and PV generation better. So specifically less wind and PV must be curtailed or stored at times of high feed-in of renewables. And basically when linking the power systems, 90% less curtailment or storage needs take place throughout Europe. Of course, as you see also for the integration scenario, there is still curtailment remaining, and avoiding that altogether would be difficult to achieve because we still observe highly correlated feed-in situations. It's also important to point out that not only cross-border grids important to enable these smoothing effects, but also we need to have enough transfer capacities within the countries. A third type of integration benefits is, I would say, a bit more a general one. Basically, it enables for all the involved countries to deal with domestic deficits and surpluses. So each country can access generation abroad, so it can import, but also it can export excess generation from domestic plants, and as such maximize security of supply, but also minimize the total cost of providing electricity. Of course, countries are either over the whole year either net exporters or net importers, but we see for all the involved countries that they show flows in both directions, both importing and exporting. Now, to summarize the main results with respect to market integration, we've seen that flexibility requirements are reduced due to geographical smoothing effects. We've also seen that this allows to minimize the curtailment or storage needs for fluctuating renewables, and it's also beneficial for countries, allowing them to both export and import electricity. Now, of course, there also remains a flexibility challenge after market integration, and this implies that we will need a more flexible power system to manage the ramps from variable renewable energies. And to do so, we need to utilize flexibility options. Two of them we have already discussed. So we have seen that indeed grids are very important with respect to flexibility because they enable smoothing effects and thus reduce the flexibility challenge. We've also seen that partial curtailment of wind and solar power is a flexibility option, but of course there are additional ones. Specifically on the supply side, a more flexible generation park, both from the conventional fossil fuel and renewable side, but of course also new service providers like demand side, response, and new storage technologies like batteries or sector integration with power to X in the longer term will be an important flexibility option. In the following now we want to focus on the generation park, so the residual power plant park, which has to then generate basically differently than compared to today. So in this graph you see the hourly load curve for the week, with the load being higher during the week and lower on the weekend. And now we of course have also wind and PV in the system, and this is then subtracted from the load, and then this blue area remains. That's the residual load which has to be met by the conventional and hydro storage power plants. And as you see, this pattern is much more erratic and volatile compared to the original load pattern. So the structure of the power plant park has to change basically. And how can we derive this need for structural changes? We utilize the concept of so-called load duration curves and residual power generation duration curves. So first of all, we take the hourly load values for the year 2030 and sort them from the largest to the lowest value, and then we get this blue curve. When we now subtract for each hour the generation from non-dispatchable renewables, we end up also taking into account imports and exports with a new value which has to be provided by the residual power plants. And when we sort these generation levels again for each and every hour, we get this pink curve. And if you compare the two graphs or lines, you see that the residual generation curve runs first of all lower and is also steeper compared to the load curve. And this then means that when we have 30% wind and PV in the system and 50% renewables in the total mix, the capacity requirements for power plants reducing more than 7,000 hours per year, this is then typically denoted as baseload power, reduce by 50%, which is of course a significant structural change. We also observe, though, that the peak load needs are reduced less strongly. So for few hours, these two curves run quite close, and this means then that it's basically mostly conventional power plants and hydro storage power plants contributing to meeting the load and the residual load. So in short, this different curve means we will need less base load and relatively more mid-merit and peak load power plants. And now this new structure of the power plant mix can also or has to also operate differently compared to today. It has to provide response to short-term output fluctuations from wind and PV, for example. But the thermal power plant park also has to provide backup for longer periods with hardly any wind and PV generation. For example, this is a week in January 2030, and you can see that this gray area, the thermal power plants, then basically generate most of the electricity consumption in that week. Now, diving into some selected country-specific results. With respect to Germany, we can say that the German power plant park is most affected in the region, not surprisingly, because it has also the most ambitious targets with respect to wind and PV deployment. And in short, the power plant park in Germany will have to ramp more often in the future. It will have to operate more often at partial load, and it has to be turned on and off more often. And how can we derive these results? In this graph, you first of all see in blue data from 2013, and on the horizontal axis you see for each hour of the year 2013 the actual generation level of the German power plant park. And it varied between 25 and some 75 gigawatts, as you can see. And when we look into the future in 2030, we see that this maximum generation reduces slightly to some 65, 67 gigawatts, but the minimum generation reduces significantly, and it reduces down to the must-run level, and we have assumed a level of 5 gigawatts of must-run in the German power system. We also see that when we compare the hourly ramps, so the changes in the production of the residual power plant park from one hour to the next, that the magnitude of the ramps does not change that drastically. Already in 2013 we had hours where the generation park had to be increasing its generation by 10 to 15 gigawatts and also decreasing. And this magnitude of ramps we also observe for 2030, but the difference is that we observe these ramps occurring irrespective of the generation level. And this means that if only a small amount of power plants are generating, some of them have to be operated in part load to provide these ramps for the next hour, and also some turbines have to be quickly turned on. These changes get even more pronounced when we look at the day-ahead stage, when we compare the generation with the change in generation from one day to the next, as here amplified or signified by 20-hour ramps. Again, the same results, that the generation level is more spread from smaller to slightly smaller maximum generation levels. But we also observe quite significant ramps in the future power system, and this pattern looks totally different than 2013. And what does it mean? Just to highlight, you might notice this negatively sloped kind of 45 degrees line, and at every single point, so at every single hour in the year 2030, the generation park, the conventional generation park, has to be turned off completely until to the next day, of course, aside this 5 gigawatts must-run level. But if you compare the pink scatter plot with the blue one, you see that indeed it's a very distinct and different pattern. So much for Germany. I now hand over to Dimitri for telling us something about the French experience.
Thank you, Christian. So indeed, France is a specific country in the zone because it is characterized today by a pretty high level of mass run, nuclear mass run, operating mostly in base load. So in 2030, the challenge faced by the French power system will be a bit different than the one faced by maybe other countries in the zone. In this graph, you see actually in 2030 a simulation of two extreme weeks and the same extreme week, but today, so in 2013 below. And what you see at this on this graph, you see that in 2030, with about 40% renewable energy, which is the assumption on the scenario, first of all, the hydropower, which is here actually, is going to play a very important role for balancing the system. It is doing it already today, as you can see here, but in the future it will do it mostly to balance change in the production of renewables. So this flexibility asset is extremely key in the French power system. You see also that in the future, in 2030, large export will continue to happen, especially in summer, where you have currently a largest export, we could say, driven by a nuclear baseload. It will continue in the future, somehow as well under the development of renewables. Nevertheless, incorporating this 40% renewable in the French power system will bring some specific flexibility challenge. You can see here, for example, in a week in 2013 summer, and you see that the base load, let's say nuclear base load, or the residual part of the park, is really starting to have to cope with flexibility. Now, we show as well in the study that nuclear power has today some flexibility potential. It has some load following capabilities. Is doing actually a primary and secondary reserve in the French power system. So this can contribute to some flexibility needs in the future. You see it here a little bit better. On the left, you see actually currently the outputs of one nuclear power plant in France during 1 week in June 2013. This power plant is Golfec 2, and you can see that the power plant is able to do up to 2 big change of output a day. And here you see actually the primary and secondary regulation, which is done basically all the time. So this potential exists technically. Nevertheless, and here it's again the scatter plot that Christian just showed before for Germany, you see that this is actually the residual part of the system in 2013 with a nuclear capacity installed of 63 gigawatt, and you will see here the change in 2030. So you have again the same effect, a reduction of the capacity which is actually needed and going to lower values, and also you see a more volatile, scattered kind of cloud, which means that the short-term operation of the residual power plant will be affected as well, but more moderately if you compare to the German case. And actually, in order to ease this, let's say, conflict between keeping nuclear assets in the French power system together with increasing renewable energy targets, several flexibility options can ease this conflict. First one being, of course, the grid integration that we have been describing before, but also demand-side management response, power-to-heat, punctilment, curtailment of renewables. And in this graph, you see that actually, if you higher the level of nuclear base load, then you would have actually an exponential generation surplus of renewables or of electricity in the power system. And the flexibility option are actually a way to go down from these two curves. So you really see a potential of flexibility reducing the excess surplus of electricity generation. I will hand out again at Christian for...
Thanks, Dimitri. We're now moving on a bit north to the Benelux region. And this region actually, of course, does not have access to large natural storage opportunities like hydro storage, for example, opposed to France, as we have seen in the French case previously. This means that the region has to manage its flexibility challenge differently. And of course, in the region of the Benelux countries, these flexibility requirements mainly arise from further deployment of wind onshore and wind offshore. And if you just have a look at this purple hourly time series, this is the time series of residual load in the Benelux region for 2030, and you can see that at some points it's actually close to the sum of the peak load in the systems, and then a couple of hours or days later it drops quite significantly and can even reach slightly negative values. So how does the Benelux region and the Benelux countries now manage this? Basically through imports and exports. It's a region which is quite well connected to neighboring countries and also increasingly so in the future. So although all the three countries are on average net importers, so they import more than the export, we also see that they also significantly export at times, meaning that this maxima or minima of residual load in the power system in the Benelux countries are managed through either export electricity flows or import electricity flows. And what's very important also for other countries is that the Benelux region is also a flexibility provider to other countries. Basically, a huge part of the flows, the cross-border flows, are actually transit flows in the region. So a flow entering the region at one border might immediately leave it at another border, being then a transit flow, and this means that then also surrounding countries can use, let's say, this power hub function of the Benelux countries to optimize their power system. So a very important geographical location the Benelux countries find themselves in. Finally, our last case study is the Alpine case of the Austrian and Swiss region, where, of course, as you might expect, hydro storage plays a crucial role for managing the flexibility requirements for the two countries, but also for the entire region. And that's basically a general and valid result, irrespective whether we look at a week with high PV generation as shown here, or a week with high wind generation and little PV, or a week with rather little PV and wind generation altogether. You notice that always these blue, dark blue areas are very well visible, and that's basically the generation from Austrian and Swiss hydro storage plants. And indeed, the simulations yield the result that the operating hours of these power plants will increase in the future. To then do a short recap and summary of the main takeaways of the study. We have seen that system flexibility requirements indeed increase, so we need a more flexible power system. And to achieve that, power system integration is very important because it mitigates flexibility needs due to smoothing effects, yielding then reduced gradients or changes of residual load, reduced balancing requirements, but also minimizing the needs to curtail or store renewable energies. Nonetheless, a more flexible power system is required, and this implies mainly a different structure of the power plant park with less base load, relatively more mid-merit and peak load plants, which also then of course has to operate differently than observed today. And aside this adjusted power plant park, of course it's also critical to get an active demand side involvement in the power market. So demand response will also be critical in the future to manage the power systems efficiently. So in short, the technical flexibility potential is large, but of course its development requires proactive policies and an enabling regulatory framework, implying that we will need a refined power market design which stresses indeed increasing system flexibility. With this, I would like to close the presentation